So welcome to RF transceiver design course. We are discussing about low noise amplifier. In last class, we leave at finding out the noise figure of the resistive feedback amplifier, common source amplifier. So we'll try to derive the noise figure. So in order to find the noise figure, we have find it out the input impedance. We have also find out the gain. So this is a gain. We have also find out the output impedance R out. Now as I told, always what we need is we need to see that how many noise sources are there. So obvious there is a RF, RS and the transistors is a noise source. So we need to consider each noise source and we need to find out the noise figure. So it is a for RF resistor we can write it down Vn square out. For RF resistor it is a straightforward 4 kT RF that is directly coming at the output. We can also write for M Vn square out for transistor, that is 4 kT gamma gm into R out square. So that is a 4 kT gamma gm. We have to find out RS plus RF square by 4. So this 4 will be cancelled out. So this is a two noise RF and M. So there is one more trick. Let us say when you are finding out the noise figure, the source noise, because the same term 4 kT RS is going to amplify and again you are going to divide it by gain square, the term will come as a 1 only. So we can directly write it as a 1, then 1 plus we can write it down 4 kT RF divided by 4 kT RS and the gain, that is R. What is the gain that we have find out? That is RF by RS. So RF by RS square so plus kT gamma gm RS plus RF square by 4 kT RS into RF by 2 R S square. So because this has a 4, we can 2 square is a 4, so we can cancel out this. We can also cancel out this, and this RS is, we can write it out 1 plus 4. This one of the RS will go up, that is 4 RS will be cancelled out, then we will get a 4 RS by RF plus, because this RF is cancelled out, RS, one of the RS will be cancelled out, so RS by RF will remain. Here again this 4 term will be cancelled out, KT will be cancelled out. We will have a gamma gm into RS plus RF square RS into RF square by RS square. So one of the term, this will also be cancelled out. So we will have a 1 plus plus gamma GM RS into RF plus RS square by RF square. So this term also here, if we try to neglect one of the term, still we can have a noise figure which is noise factor which is equal to 2, and in terms of dB it is more than 3 dB. So this amplifier, it has a little bit lesser noise compared to the previous structure. However, it also suffers from a higher noise figure and the reduction in the gain. So we need to have another topology. So the third topology, that in these two topology we have seen a common source amplifier. Now we will go for the common gate amplifier. So this configuration has a higher noise figure. So now we are going for the common gate amplifier. So let's try to find out the same input impedance, output impedance, and the gain and noise of the amplifier. So for common gate, so this is a VB and we will have a RS source resistance, Vs, and there is a RD, this is a VDD. So because this is a common gate amplifier, if you try to see the input impedance from this side, the in this case is also 1 by Gm. So input impedance we got, that is Rin 1 by Gm, and if we try to find out the noise performance, so the gain is also straightforward for this, Gm into Rd, that is the gain, and what we output impedance, because directly it is by seeing the output, it is the Rd, because if there is a here while calculating we are not considering channel length modulation. If you consider the channel length modulation, you also need to consider the output impedance Ro. So here output Ro is Rd. So if we try to draw this again, Rd, what is the noise? If we show the noise in terms of the voltage, Vn square, which is equal to given by 4 kT gamma by Gm, and then we have a Rs. So if we try to see the structure in this way, if your noise is as this is a common gate configuration, but if you try to see the noise voltage generated thermal noise by the MOSFET, it is 4 kT gamma by Gm. You can write the gain in that case can be replaced as a Gm Rd by 1 plus Gm into Rs, where source Rs is a source resistance. So if you consider this and this is multiplied with the output resistance Rd, what we will get is noise Vn square out due to the MOSFET is given by 4 kT gamma by Gm into gain square Gm Rd by 1 plus Gm Rs whole square. And if we consider Gm equal to 1 by Rs, we can get this as a 4 kT gamma by Gm into Gm square Rd square by, that will come by 4. This can be written as a kT gamma Gm into Rd square. Or if we try to consider the Rs is equal to 1 by Gm, in that case we can also mention it as a kT gamma Rd square by Rs. So this can also be mentioned it like this. So noise figure then can be given. So if we try to use the same equation as before, we can get a noise figure which is equal to 1 plus kT gamma, that is Rd square by Rs by 4 kT Rs into GMRD square plus we will have a Rd also GMRD 1 plus GMRS square. So here we can cancel out if Gm is equal to 1 by Rs. So that term will be 2. So this 4 will be cancelled out. Then if we consider this Rs will be cancelled out, Kt will be cancelled out, Rd square will be cancelled out, and Rs square if is equal to 1 by Gm. So we can get is only the gamma. So the final noise figure is given 1 plus gamma. In this case this 4 kT will be cancelled out, this will be 2, so that will come up, it will be written as a plus 4 Rs by Rd. So if we write it down here, the final noise figure is given by 1 plus gamma plus 4 Rs by Rd. So we can see that here by using this configuration we can little bit reduce the noise, but if we consider the gamma is equal to 1 and then this noise figure again is 2 plus 4 Rs by Rd. So advantage of this configuration is all these three configuration, considering the resistive matching, the first, second feedback, resistor feedback in common source and this common gate configuration, all these three configuration, it has a high noise figure. However, it can be used for the wide band application where you have a not stringent requirement of sensitivity or noise figure, for example IoT, and it can also be have a better impedance matching is also wideband. So now how can we reduce the noise figure? This is a question. In order to reduce the noise figure, we need to get the input impedance of 50 ohm, that is a resistive, without using a resistor. Can we do that? Without using a resistor, can we get input impedance of our desired value? Let us try one topology. So, in this case, you just stay with me. Here, if you have a ZS, means this is a your MOSFET, and you have connected the impedance ZS, and if you want to consider the Z in, so we can write a Z in, and if there is a CGS capacitor, so you can write it down Z in, which is equal to ZS plus 1 by SCGS, that is due to the capacitor, and you will get a GM into ZS by SCGS. So, this is the input impedance of the common source, means amplifier, where your source is has a ZS. So, this Z in, which is that can be find out Z in easily if there is a CGS and there is a ZS. You will have a current which is flowing, that is a GM into VGS. So, here the first is a ZS plus this capacitance SCGS, and when this flow this current will flow, we will get a GM by ZS, GM into ZS. So, GM by SCGS, because the voltage here is nothing but 1 by SCGS VGS across the VGS. So, we will get a Z in, which is a ZS plus 1 by SCGS plus GM ZS into SCGS. Now, in this term, if we try ZS is equal to RS. So, we will try to replace ZS here, we will try to replace the ZS with different value ZS equal to RS. So, if we replace ZS is equal to RS, we will get RS plus 1 by SCGS plus GM into RS by SCGS. So, this term here is looking as a combination of a resistor and a capacitor. So, we are not going input impedance which is a purely resistive, we are getting it is a combination of resistance and a capacitor. Now, if we try to replace the ZS with 1 by SCS, that means if ZS is a capacitance which is denoted by CS, we will get Z in, which is 1 by SCS plus 1 by SCGS GM by S square CGS into CS. So, this will come to the negative resistance, and as we have already discussed the stability, we need to avoid the negative resistance. So, as we are adding the negative resistance, it leads to the instability. So, we can also not use a capacitor here. Now, we have a third choice, that is a inductor. So, if we try to put here Zs, which is equal to SLS, which is given by J omega Ls, and then we can get the Z in, which is equal to J omega Ls 1 by J omega CGS GM Ls by CGS. So, here this term itself is a resistive. In the previous one of the place, we got the resistive term, but again this resistance will add a noise, that we have already seen in the previous 2-3 configuration, that we want to avoid the resistance and we want to get the input impedance 50 ohm. In this case, GM Ls by CGS, it is a resistive term, and if we try to replace GM by CGS, we have already define omega t, which is equal to Gm by Cgs. So this can also be written as a omega t into Ls. Now this term here, we can see that if this is a resistor, this is nothing but a resonant circuit, RLC resonant circuit, and we have talked much about the resonant circuit. So if we know the resonant, if we have a resonant circuit, we have a omega naught f naught resonance frequency, which is given by 1 by Cgs plus multiplied by Lg plus Ls, because there are a 2 if here. So in the previous case, we have not in this equation there is a no Lg, but here if we try to add the Lg, then it will be Z in equal to 1 by j omega Cgs plus j omega Lg j omega Ls plus Gm Ls by Cgs. Now why we added a Lg in series? Because Ls is going to determine already the resistance, that is the omega t Ls. Now if we want to have a freedom in terms of the tuning frequency, then it is better to use a Lg. So we are connecting Lg in series, and it will help us to do the matching as well. So at resonant frequency f naught, we will have a resonance, that is 1 by Lg plus Ls into Cgs, and at that time you will have input impedance, which is a resistive, because during the resonance your input impedance is this, that is given by omega t Ls. So you need to make omega t into Ls equal to 50 ohm. So you can directly match the antenna, means antenna 50 ohm impedance or source impedance 50 ohm without using a resistor. Only you need to choose a Ls such that it will provide you the omega t into Ls equal to 50 ohm. Now here your as this is a resonant circuit, series resonance, you can write a Q, that is omega naught L by R. You can also get, that is R here is Rs in plus omega t Ls. So now again we are adding the source resistance, and then you have L, which is Lg plus Ls. So if we see the effective Gm at the f naught, so if this is your MOSFET and this is a Cgs capacitor, at the, we already have discussed that during the resonance the voltage, and at that time I also told that we will use the same equation again. So if we have a voltage, if we want to find the voltage across capacitor or voltage across inductor during resonance, it is nothing but Q times of V in. So that is why it is a Q times of V in. The Vgs is equal to Q in into Vs. So we will get V in, which is again, because there is a resistance division, omega TLS by our Rs plus omega TLS. If omega TLS is equal to Rs, it is given by Vs by 2. So you will get Vs, which is equal to 2 into V in. So you will get a Vgs, which is 2Q, because your Vgs is equal to Q in into Vs. Vgs, you will get a 2Q in into V in. So your ID current, that is a Gm into Vgs. So you can directly write ID, which is a 2Q in Gm into V in. So that Vgs you can directly replace with the 2q in V in into Gm. So this 2q in V in q in into Gm, we can also mention it as a transconductance of this circuit Gm Id by V in equal to 2q in into Gm. So if you know the transconductance, now what you need is a uh, output impedance. So the gain is nothing but, so this gain is nothing but transconductance Cm into R out. Now in this case we are totally replacing the resistor. So at the load, if you connect the inductor, that is LD, so LD is parallel to the CD. Now this CD is a combination of capacitor. There is a possibility the capacitor from at this side drain to gate, and then there is a bulk also, so another capacitor here also. So all the capacitor and output capacitance, if you are going to drive some capacitive load, so C out also, this all comprise in the CD. So when there is LD and CD, this also represent, because all these are not will be the ideal. So this will represent the resonant circuit, and for that resonant circuit you can find the Rp, that is a resistance Q into LD by CD. So this is a Rp. So the total gain, your voltage gain, is given by 2q in Gm into Rp. Now here we need to maintain F naught for 1 by 2 pi LD into CD, and F naught at the input side, and at this is, if we consider this is at output, and if this is at input, it should be match. Then only it will give you the maximum gain at your desired frequency of F naught, and at input side also it will be match, and at output side also it will provide you the resistance Rp, and you will get the resonance at that Rp resistance. It should have a resonance. During the resonance you will get the parallel resistance Rp. So this is how this source degeneration common source amplifier is work, and it is widely used LNA in the field of RF transceiver design. So this is same design can be extended to the cascode. So here we have only used a single transistor. Now because of the CGD transistor, CGD capacitor, because of the CGD capacitor and LD, there is a possibility of the negative resistance, and that can be reduced by adding one more stage, that is a cascode, that is called a cascode amplifier. So before going to the cascode, we will try to find out the noise figure of this common source LNA. That is, if we want to find out this noise figure, the I out is given by, in this case if we want to find out the I out, it is given by Gm into VGS. So there is I out has a two current Gm into VGS and the noise current In. We can write V in, which is equal to Rs plus Lg as. So if we make a equivalent circuit here, so this is a Lg, there is a Rs capacitor, CGS, Ls, Gm into VGS, and the current In, this is a I out. So if we want to see the V in, we will get Rs plus Lg into S. This current through this is nothing but Vgs into 1 by S CGS. So, that will be Vgs into S CGS. So, this is the current that will flow, plus this voltage Vgs plus the voltage drop across this Ls. Now, Ls will get two current I out and Vgs into CGS into S. So, this current is the current which is flowing here, and current that is flowing from here, that will be added Vgs. Now, we already have I out Gm Vgs plus In. So, we can write it down a Vgs. So, in this equation, this Vgs, we can get I out minus In by Gm. So, same thing we can mention. So, if this is I out, we will get here j omega naught Ls, and that will happen at the resonance frequency omega naught. So, what we write I out j omega naught Ls plus j Rs Cgs1 omega naught by Gm minus In. So, same Vgs we have mentioned here, j Rs Cgs omega naught by Gm. So, this is a Vn in terms of I out. So, we will get a Gm, that is a transconductance I out by Vn Gm out equal to 1 by omega naught Ls plus Rs into Cgs by Gm. So, this will happen when we have a resonance. So, during resonance we will have a I out by V in, that we can mention it as a 1 by omega naught into Ls plus Rs. So, omega naught we can take it out this, and other term will be 0. So, that is why we are considering only this Ls plus Rs Cgs into Gm, that is a Gm out. So, we can write a G out equal to omega t by 2 omega naught into 1 by Rs, because we can get omega t, which is omega t into Ls equal to Rs. So, and Gm by Cgs in this case is equal to omega t. So, here Gm by Cgs we can write omega t. So, omega naught by omega t, and this omega t Ls is nothing but Rs. So, omega t by 2 omega naught into 1 by Rs. So, this is the output transconductance. So, Gm by Cgs here is omega t, and the output current, noise current, can be written as In out M, that is In by 2, and that we can directly write 4 kT gamma Gm as a kT gamma into Gm if we consider the square. So, here In out, this In out can be considered as a In1 by 2, half of the current that we are considering, and In square out, which is kT gamma into Gm. So, your noise figure can be written. So, in the previous case we have considered the noise figure, which is equal to 1 plus Vn square out, and we divide it by gain. Now, in this case we are considering the In square out, and we are dividing it by Gm out square. So, this In square out, that is a kT gamma Gm, that is In square out is given by kT gamma Gm. If you try to put this value, and the G out is nothing but omega t by 2 omega naught 1 by Rs square. So if you consider the G out square, so if we try to write it down, 1 plus kT gamma gm divided by 4 kT rs into omega t by omega t square by 4 omega naught square into 1 by rs square. So this rs will be cancelled out, kT will be cancelled out, 4 will be cancelled out, we will get the same 1 plus gm rs gamma omega naught omega t square. So in this case, this noise figure equation is directly relating to the only the noise generated by the source resistance Rs. So this is not in your hand, and by the transconductance Gm, that is a inherent noise of the MOSFET. This is a process dependent parameter, and omega naught by omega t. The same equation also we have seen when we have defined the inherent MOSFET noise, and that also is depend upon the inversely proportional to omega t. So as you increase the omega t, reduce the noise figure, and you will get the better noise performance. So this circuit will provide you the optimum noise figure with the desired gain. We will discuss about the cascode. As I told, this has a limitation. We will discuss about the cascode in the next class. Thank you.